In this video, we're going to learn how we can predict the amount of product that is going to be produced by a chemical reaction based on all of the different amounts of reactants that we're starting with. So we essentially already know how to do this if we're only considering one amount of reactant. In the previous video, we talked about how, if you have this many grams of this reactant and all of it reacts, you can figure out how much product is going to be produced. But when you have multiple reactants of limited quantity, one of them is going to run out first. So this video is about how we figure out which reactant is going to run out first. And that reactant is what we refer to as the limiting reactant. So that is the reactant that is completely consumed in the chemical reaction. And when your limiting reactant runs out is when your reactant stops. No more product can be made once you've run out of one of your reactants. So the limiting reactant is the one that really controls the maximum amount of product that can be made. We may have, a ton of one reactant and only a little bit of the other. That one that we only have a little bit of, once it runs out, the reaction's over. And it doesn't matter how much more of the other reactant we add. Once the limiting reactant is gone, we've made as much product as we're going to make. The other reactant or reactants are referred to as excess reactants. And this is just anything that is not completely consumed in the reaction. So some of this will be left unreacted when the reaction is finished. So limiting reactants and excess reactants can be a little bit confusing, a little bit complicated. So I like to start with an analogy. So please bear with me for this analogy. Chemistry is really just cooking. So let's imagine instead of a chemical reaction, you're throwing a party and you want to bake some cakes. And you go home and you rifle through your kitchen, you rifle through your pantry and your refrigerator to see how much of all of these different cake ingredients do I have, and you want to figure out how many cakes can I make for this party that I'm going to throw. And your recipe is for a very traditional pound cake, to keep things simple. A very traditional pound cake requires 1 pound of flour, 1 pound of sugar, 1 pound of butter, and 1 pound of eggs. Hence the name pound cake, is where that comes from. And you go through your kitchen and you find a bag of flour, a new bag of flour that says it's 5 pounds. Cool. You find a new bag of sugar that says it's 4 pounds. You look in your fridge and you find 6 sticks of butter and 2 dozen eggs. So you will notice that a few of these we have like some unit mismatch. We have a pound of butter versus sticks of butter, and we have a pound of eggs versus dozens of eggs. So we're going to need some conversion factors in here, but that's okay. We know how to convert units. I will tell you that 1 pound of butter is 4 sticks. Typical box of butter that you buy at the grocery store is a pound of butter. It contains 4 sticks of butter. A pound of eggs is really kind of a weird way to measure eggs. Not usually how we do it. Eggs, being a natural product, are not super standardized in their weight, so it can vary a little bit. But for the purposes of simplicity, let's say that a pound is around 9 eggs. It's usually between 8 or 9 large size eggs, which is what most people tend to buy. So let's say it's 9. We can now start to convert things a little bit better. So if we want to figure out, based on each of these ingredients, or overall, how many cakes can I make? What we really need to think about is how many cakes can I make based on each of these ingredients. So if I have 5 pounds of flour in my kitchen and each cake needs a pound, I could, if I had an unlimited amount of everything else, turn 5 pounds of flour into 5 cakes. Same idea for sugar. I have 4 pounds, each cake needs a pound. If I had an unlimited amount of everything else, I could turn 4 pounds of sugar into 4 cakes. With the butter, we've got 6 sticks available to us. Each cake needs 4, so if we're just looking at whole cakes, I can only make 1. I would have 2 sticks of butter left over, but that's not enough for me to make a whole nother cake. And doing a half batch requires adjusting times and temperatures of baking and stuff, and maybe you're not super comfortable doing that. So we're looking at whole cakes, so we could follow the recipe as written here. So we only have enough to make 1 cake, singular. For the butter, 2 dozen eggs, we know that a dozen is equal to 12. So this means we have 24 total eggs. If each cake requires 9, 24 eggs is going to be enough to make 2. To make 2 cakes, we would need 18 eggs. To make 3 cakes, we would need 27. We don't have 27. So we have enough eggs to make 2 cakes with 6 left over. So looking at our ingredients compared to our recipe, we see that with what we have available, once we make 1 cake, we're out of butter, which means it doesn't matter that I have 5 cakes worth of flour. I can't make 5 cakes because I don't have enough butter to make 5 cakes. So in this analogy, the butter is my limiting reactant. That I run out of butter, I can't make any more cake. We're only having 1 cake at this party. So I would have a bunch of other stuff left over, but without butter, you'd have a pretty gross cake. So if you tried to make any other cakes, they would not be good. They would not be cake without butter. So that is our limiting reactant. Everything else would be considered excess. Once I made my 1 cake, I would still have 4 pounds of flour left over in excess. I would have 3 pounds of sugar left over in excess, and I would have 15 eggs left over in excess. But the butter is my limiting reactant because once it's gone, I can't make any more cake. So I know this seems a little bit silly to be talking about cake, but what we're doing with stoichiometry in the rest of this video is exactly the same process. It just feels harder because the numbers are less nice, the numbers aren't generally integers, and the units are a little bit more unfamiliar. But it's literally exactly the same process. What we're going to be doing to determine our limiting reactant is figure out, based on the amount of reactant I'm starting with, based on the amount of ingredient I have available, how much product can I produce? How much cake can I make? Whichever one produces the least is our limiting reactant. Because once I hit that amount of product, that amount of cake in our analogy here, I'm out of one of my ingredients and I can't make any more. So the limiting reactant is the one that produces the least amount of product. And so we're going to go through the same process just for chemical reaction instead of cake for our party. So switching gears back to lab chemistry and not kitchen chemistry, we can apply these same ideas to a chemical reaction. If 5 grams of hydrogen and 45 grams of oxygen are combined and allowed to react as completely as possible according to the reaction below, we want to identify what is the limiting reactant, what is the maximum mass of water that can be produced, what is the mass of excess reactant that remains. So comparing this back to my cake analogy here, these are my available ingredients. This is what's in the kitchen. This is what's available in my science kitchen here. Oops, don't know what that is. And we want to figure out which of these is going to run out first. And we do that by figuring out how much product could I make if I react all 5 grams of this with unlimited oxygen, how much product do I get? If I react all 45 grams of this with unlimited hydrogen, how much product do I get? And whichever one is less will be our limiting reactant. Keep trying to move, oh, what did I do? Interesting. I'm trying to move this down so we can answer this one part at a time. Beautiful. So to find what is our limiting reactant, we want to determine which produces the least product. So this is going to be exactly like what we were doing in the last video of figuring out how much product can I produce from a particular amount of reactant. We're just doing it twice. We're doing it once for each of our reactants. So we are told that we are starting with 5 grams of hydrogen. And we know that basically the first thing we always need to do in stoichiometry is convert to moles. So we would have 2.016 grams of hydrogen is equivalent to 1 mole of hydrogen. That is our molar mass of H2. And then we are not interested in moles of H2, we are interested in moles of product. And we can see from our chemical reaction that 2 moles of hydrogen reacts to produce 2 moles of water. So we have grams of H2 canceling grams of H2. We have moles of H2 canceling moles of H2. And that leaves us in units of moles of water, which is what we are interested in. You could also convert to grams here, but it's not strictly necessary. Whichever produces more moles of water will also produce a larger mass of water. So you can look at it either way. So we'll keep the calculations to a minimum and not convert to grams. So 2.48 moles of H2O would be produced, and this number is assuming that all of the H2 available reacts, i.e. if the H2 is limiting. We need to do exactly the same calculation then for O2. We have 45 grams of oxygen, so we need to use the molar mass of oxygen to convert grams of oxygen to moles, and then use our coefficient ratio to convert moles of oxygen into moles of water. Make sure you are always converting to moles of the same product if there is more than one. It doesn't technically matter which one you choose, but you do need to be comparing the same thing. So once again, checking on our units to make sure everything is set up properly. We have grams O2 on the top and grams O2 on the bottom that will cancel. We have moles O2 on the top, moles O2 on the bottom that will cancel, leaving us in moles of water, which is exactly where we wanted to be. So we find that 2.81 moles of H2O would be produced if all of the O2 reacts. So looking at this, we see we can produce about 2.5 moles of oxygen with all of the H2 we have available to us. We could produce 2.81 moles of water with all of the O2 that we have available to us. So what this means is that once we have hit 2.48 moles of water produced, we are out of H2. We have used up all of the hydrogen available to us, and that reaction has to stop. We can't actually get all the way to 2.81 because we ran out of hydrogen once we got to 2.48. So this one produces less product. So this means that H2 is our limiting reactant. So thinking back to the cake analogy, we ran out of butter. We had plenty of extra flour. There was enough flour for 5 cakes, but we couldn't make 5 cakes because we ran out of butter after 1. Same idea here. We can't make this many moles of water in reality because we run out of hydrogen first. So the hydrogen is gone once we've produced 2.48 moles of water, which means that the hydrogen is going to be our limiting reactant. The next part of the question asked us what is the maximum mass of water that can be produced. We've mostly already solved for this. So this is going to be the actual amount of water that is produced by the reaction. We did it in moles in the first step, so all we need to do is convert that number into grams since we were asked for the maximum mass. If you had done this all the way through to grams up here, you would literally already have the answer in front of you. So we ended up having to do that math eventually, but we only have to do it once instead of twice now. So we know that our limiting reactant allows us to produce 2.48 moles of water. We just need to use the molar mass of water, which is 0.15 grams of water is equivalent to 1 mole of water. We see moles of water on the top, moles of water on the bottom, so our units cancel, leaving us in grams, which is exactly where we want to be. And that is about 44.7 grams of oxygen. The last part asks us what mass of excess reactant remains. So for this one, we need to do a little bit more work. What we need to figure out first is how much of that other reactant was consumed. So first we need to determine how much O2 was consumed, then subtract that from how much we started with. So determining how much was consumed is a stoichiometry problem we've done before. We're just converting mass of H2 into how much O2 needs to react with that. So since we know that hydrogen is our limiting reactant, we know that all 5 grams of that is going to be consumed. All of that is going to react. And we're looking to find how much O2 is needed to react with that. So first thing, as always, is convert to moles using the molar mass. Then we need to convert from moles of hydrogen into moles of oxygen. So moles of oxygen is going to go on the top, moles of hydrogen is going to go on the bottom, and we're going to fill that in with our coefficients from the reaction. 2 moles of hydrogen reacts with 1 mole of oxygen. So the 2 goes on the bottom and the 1 goes on the top with the way our units need to be set up. And then last but not least, we can convert that to grams using the molar mass of oxygen, which is 31.998. So we can see that grams of H2 cancels grams of H2, moles of H2 cancels moles of H2, and moles of O2 cancels moles of O2. And we are left with units of grams of oxygen, which is where we want it to be. So we find that about 39.68 grams of O2 were consumed in the reaction. So important to keep in mind what we are calculating is how much reacted. We're asked how much was left. We started with 45 grams. We consumed 39.68 grams. So that means we have about 5.3 grams of oxygen left over at the end. What was I going to say? I don't remember. So for the most part, this should feel very familiar to the previous video, the same types of calculations going through the same process of converting grams to moles of one thing, then moles of that to moles of something else, then as needed, moles of that to grams of that substance. Just adding on a little bit of extra piece of figuring out what reactant is actually going to run out in this reaction, what is controlling the amount of product I can produce, and then how much stuff is actually going to be left unreacted at the end. end of my reaction.